Bismillahirrahmanirrahim. We continue our discussion in CPU scheduling. In previous lectures, we started this chapter and discussed some of the concepts related to CPU. As you know, CPU is a resource within your system, and generally, single CPU is provided to service so many applications, one after another. So a single CPU is multiplexed among different applications. Let's have a recap of the topics that we had discussed in previous lecture and carry forward the discussion from there. In previous lecture, we revised some of the concepts related to CPU scheduling. We discussed what is CPU scheduler or short-term scheduler. It is the type of CPU scheduler is the type of scheduler that selects which process should be sent next to the CPU from the ready queue. It actually shuffles or organizes the ready queue, which is your RAM. The processes which are to be sent first are placed at the top of the ready queue, while the processes which are placed at the bottom are those which are to be executed or which are to be sent to CPU later. We then discussed the dispatcher. Dispatcher is actually a CPU or an operating system routine or a function that assigns CPU to the process that has been selected by the CPU scheduler. So dispatcher actually performs the dispatching functions. That means it sends the process to processor for execution. Now, which process is sent to the processor? The one which has been selected by the CPU scheduler. Then we discussed different criteria on the basis of which your system performance is generally measured. And on those criteria, different CPU scheduling algorithms are then designed, which we will be discussing in today's lecture. 5 different criteria were discussed, which were CPU utilization, and we said the CPU should be utilized as much as possible. Maximum CPU utilization should be ensured, though 100% CPU utilization is not achieved due to dispatch latency. Second criteria was throughput. Now, throughput is the number of processes that complete the execution in defined unit time. So the more number of processes are getting completed in defined unit time, the more your system performance is considered good. So throughput should be maximum. Third criteria that we discussed was the turnaround time. Turnaround time was the time it takes for a single process to complete its execution. So turnaround time considers single process, while throughput considers total number of processes. So we would like to have a processor which takes less time to complete a single process. So a single process should take less time to get its execution completed. This criteria, turnaround time, is kept minimum. Fourth criterion was the wait time. It is the time a process has been waiting in the ready queue. The more a process is kept waiting in the ready queue, the more system performance will go down, the more CPU will be idle. So we would like to have a system in which processes are getting executed at a faster rate. So less CPU, less process waiting needs to be done in RAM. So wait time needs to be minimized. The last criterion was the response time. Response time is the time during which the system generates first response when your process is submitted to the processor. It may not be the final results, it may be some initial results, it may be some error message, it may be some request from your process. But the first response is generated in how much time, that particular time is known as the response time. So it would like to have a system that generates quick responses as soon as we submit a process. So the processing response time should be minimized. Among 5 criteria that we discussed, 2 of them, which were the CPU utilization and throughput, should be maximum, while rest of the 3, which are the turnaround time, the wait time and the response time, they should be minimized. So these were the topics that we had discussed in the previous lecture. In today's discussion, we'll move forward with the scheduling algorithms and discuss different scheduling algorithms with examples. These scheduling algorithms are basically to schedule the CPU on the basis of some already defined criteria of execution. The CPU scheduling criteria that we had discussed in previous chapter needs to be fulfilled by these algorithms in order to be selected by your operating system. So every algorithm is executed on the basis of its own terms and conditions. We will see those terms and conditions, but they must ensure to fulfill those 5 criteria that we had already discussed. Let's proceed with different CPU scheduling algorithms and see how they respond in different situations. First algorithm is known as, or is given the name as, first come, first served scheduling algorithm. That clearly defines its working mechanism. That means whatever the process is, no matter how long it is, no matter how short it is, whichever process comes first in the RAM, that process should be given to CPU first. So first come, first served explains its sequence of execution, or it explains its sequence in which CPU will be assigned to different processes by its name. Whatever process comes first in RAM, that process will be sent first to CPU. So, in whatever order processes are arriving in RAM, in that specific order, they are then sent to processing on CPU. Let's consider an example how this first come, first served algorithm will take its shape when it is implemented in the system. Let's suppose we have the ready queue. This is the shape of the ready queue. 3 processes are waiting in queue within the ready queue. First process that has arrived first is known as P1, process 1. After P1, P2 arrives, and after P2, P3 arrives. So these 3 processes are waiting in queue within the RAM. This is the burst time. Burst time is actually the CPU burst time. As you remember in previous lecture, we discussed a process has 2 types of burst in its complete life cycle. Sometimes it executes on CPU, that is known as CPU cycle or CPU burst, while some other time it requires IO cycle, that means it has to be executed on some IO device. So that is known as its IO cycle or IO burst. So IO cycle or IO burst and CPU cycle or CPU burst are within any process. This is the common structure of a process life cycle. But here in this case, since we are studying CPU scheduling, so we will be considering only their CPU burst or CPU cycle. So the first process that arrives in RAM, which is P1, has a CPU requirements of 24. That can be milliseconds, that can be microseconds, but instead of considering units, we are just considering the time. So first process P1, which has arrived first in RAM, it requires CPU for 24 unit time. The second process is P2, which comes a second in RAM. It requires a CPU for 3 unit time. And the third last process is P3. It also requires CPU for 3 unit time. Now the algorithm, as it says, whatever the process comes first, CPU is assigned to it first. So the first arriving process is P1. Now we have to see the performance of this algorithm by drawing a giant chart. Generally, giant charts are used to track the performance of your projects. So in this case, the algorithm performance of this algorithm, first come first served, is also tracked using giant chart. So this is the structure of giant chart. Here, as you can see, this is the structure of giant chart for this algorithm. This chart actually shows the CPU execution time. How much time CPU has taken to complete the execution of these 3 processes. Now keep in mind, whenever CPU starts its execution, its time is always considered from 0. CPU time is always counted from 0. Whenever a CPU starts execution, its time is counted from 0. Now below the bar, below this chart, these numbers represent the total time taken by CPU. Total time taken by CPU. These numbers 0, 24, 27 and 30. This shows the total time taken by the CPU to complete these 3 processes, while above these bars represent different processes which are to be executed on CPU. Now, as I just said, CPU time must start from 0. The first process that has arrived in RAM is P1, and it requires CPU for 24 unit time. So right from 0, P1, as soon as this process has arrived, CPU has been assigned to it. CPU time is counted from 0, and from 0 to total number of time, which is the burst time, CPU burst time of P1, that is counted, and for that number of time, for that amount of time, CPU has been assigned to P1. So right from 0 to 24, this unit time of CPU has been given to P1. During that time, during these 24 seconds, rest of the 2 processes, P2 and P3, are waiting in RAM. So that is their wait time, which is then getting calculated or counted. When P1 is executing on CPU, the other 2 processes are waiting in RAM. Now, as P1 completes its execution of 24 unit time on CPU, it goes out And the next process which is now has to go to CPU is process 2, P2. Now right from where CPU has stopped one process, right from that place another process starts its execution. Since its time is 3 unit time, so 24 plus 3, 20 total CPU time utilized is 27, though this 27 unit time actually shows CPU has completed the execution of two processes by 27 unit time. But here you can see the slots. We have differentiated different processes with the help of these bars. So at 24 unit time, P1 has stopped, and right from there P2 starts its execution, and after completing its 3 unit time at 27 unit time, P2 is stopped. CPU time is getting counted, it is being added, but the processes times are getting stopped by these bars. As you can see here, these are the bars I have drawn. Now after P2 has completed its execution, it goes out, and the last process in the RAM is P3, whose time is 3 unit time. So 27 was the time where P2 has stopped its execution or completed its execution. So right from 27, P3 is assigned to CPU, and it completes its execution for 3 unit times. 27 plus 3 is 30. So it completes its execution of 3 units, and the overall CPU utilization is 30 unit time for 3 processes. But individual process execution has been defined separately. First process took 24 unit time, second process took a total of 3 unit time, that collectively makes a 27 unit time of CPU, while third process is getting completed at 30 unit time of CPU, though its own time is just 3 unit times. So where one process is completing or getting finished, right from there we are starting another process. Now this is how we draw the giant chart. You can see CPU utilization is achieved at 30 unit time. During these 30 unit times, 3 processes have been completed. That means, considering 30 unit time, we have tried to make the system execute 3 processes during this defined 30 unit time. So the number of processes getting executed in 30 unit time are 3 using first come first serve, which is the criteria known as throughput. So during 30 unit time, 3 processes are getting completed. Now what was the turnaround time? Turnaround time was the time taken to complete a single process. Now P2 is getting 24 unit time to complete its execution. P2 is getting 27 unit time to complete its execution, and P3 is getting 30 unit time to complete its execution. So individual time is also counted, and overall CPU performance is also calculated. Now the important thing is the wait time, the amount of time a process has been waiting in the ready queue. Let's calculate the wait time for the 3 processes. Wait time can also be calculated from the giant chart. So here you can see the wait time for process P1 is 0. Why? Because as soon as the process 1 has arrived, CPU has been assigned to it. So here you can see, as soon as CPU has started its execution from 0, P1 has been assigned to it. So P1 has not waited a single unit time within the RAM, so its wait time is 0. Now the wait time of process 2 is how long process 2 is been waiting within RAM. So this is the time by which a process P2 has been waiting in RAM. So how much time P2 has taken to wait? It is 24 seconds. As you can see, from 24 seconds CPU has been assigned to P2. That means it has been waiting in the RAM for 24 unit time. So P2 is waiting here for 24 unit time. Last process is P3. Now how long P3 has been waiting in RAM? Here you can see CPU has been assigned to P3 at 27 unit time. This is P3 and CPU has been assigned to P3 at 27 unit time. That means P3 has been waiting in RAM for 27 unit time. That can be milliseconds, that can be microseconds, but we are not considering the units. We are just taking it as unit time. So P3 has been waiting 27 unit times within RAM for its turn to be assigned to CPU. Now let's calculate the average wait time. How average can be calculated? All the three wait times are added together and divided by the total number of processes. So you can see 0 plus 24 plus 27. These are the three wait times for three processes, P1, P2 and P3. And since there are three number of processes, so the total is divided by the number of processes, which is 3. The average wait time becomes 17. That means on average, a process has to wait for 17 unit time in RAM for its turn to be assigned to CPU. Now this 17 could be milliseconds, 17 could be nanoseconds, 17 could be microseconds, 17 could be seconds. Depends on the performance of the system. So I hope first come first served algorithm must be clear to you and how you have to draw the giant chart. Keep in mind the bottom numbers are showing representing the CPU time, while the bars at the top of these numbers are showing the processes. So processes are stopped with these bars here, as you can see, but CPU time is continued here. You can see like that. CPU time is not stopped. Now, let's reformulate this or redesign this algorithm. Since 17 unit time is quite a lot of wait for a process, so we now need to optimize. As we said, the wait time should be minimized. The criteria, the optimization criteria that we had discussed last time, that wait time should be reduced, should be minimized, but 17 unit time is quite a lot of wait time. So now we have to modify this algorithm in order to reduce the wait time, since our optimization criteria says that wait time should be minimized. So what can we do? We now shuffle. The CPU scheduler actually shuffles the RAM. So here you can see it shuffles the RAM like this. P2 is placed first, then P3, and at the tail is placed P1. This shuffling has been done by CPU scheduler, as I discussed in previous lecture. Why the shuffling has been made? Because the wait time was too much and we want to minimize or reduce this wait time. So the CPU scheduler or the short-term scheduler shuffles the ready queue. Now as you can see, P2, the CPU cycle of P2 was 3 unit time. The CPU cycle for P3 was also 3 unit time. That's why they are organized one after another the way they had arrived earlier. And the longest process which required a lot of time on CPU was P1, which was 24 unit time. So this was the sequence. In previous case, P1 was placed at the first location, P2 was placed as second, and P3 was placed at last. But now, since wait time is too much, so we had reformulated the algorithm, and CPU scheduler shuffles the RAM. P2 and P3 have the same CPU time, so their sequence has not been changed. They are kept as they had arrived. First come, first served. So in whatever sequence you place them, either you place P3 first or P2 first, the response will remain the same since their CPU time is same. But P1 is quite a heavy process that requires a lot of time on CPU that has been placed at the end. Now let's see the structure of the giant chart. We draw giant chart again. Here you can see CPU time starts from 0. As I said earlier, the first process which is in RAM is P2, and the time for P2 is 3 unit time. So starting from 0, 3 unit time has been given to P2. So here P2 completes, it is stopped by the operating system, and the next process which is in RAM is P3. P3 is given CPU control of CPU. It takes also 3 CPU unit time. So starting from 3, it executes till 6 unit time of CPU. A total of 3 unit time has been given to process P3. So at 6 unit time of CPU, P3 completes its execution. It is stopped here with this bar, as you can see, and the last process which is in RAM is P1. So CPU has been assigned to P1, and it requires 24 unit time. So starting from 6 till 30, it takes a total of 24 unit time to complete its execution. If you add 6 with 24, the result would be 30. So if you compare both the example in the previous case and this one, the total CPU time is again 30. In 30 unit time, total number of 3 processes are getting completed, same as the previous one. But the change is evident in the wait time. Here you can see, along with other factors. For example, the turnaround time, if we consider turnaround time in this revised first come first served algorithm, so you can see P2 is taking 3 unit time to complete its execution, P3 is taking 6 unit times to complete its execution, and P1 is taking 30 unit time to complete its execution. During 3 unit time, in previous first come first case, the example that we had discussed earlier, during 3 unit time of CPU, no process was completed. Even during 6 unit time of CPU time, still no process was completed. The first process that got completed was at 24 unit time in previous case of first come first served. But here you can see time has been reduced. The turnaround time has been minimized as well in this case, which was also an optimization criteria, that turnaround time should be minimized. Though CPU utilization and throughput is same in both the cases, but the turnaround time should be reduced, and we have reduced the turnaround time. Now let's calculate the wait time. So for process 1, if you consider the wait time for process 1, this is process 1. Let me clear the diagram. The first process is process 1. The giant chart is helping you to calculate the wait time. Here you can see the time the process 1 has started its execution, so it is the unit time 6 from where CPU has been assigned to P1. So how long P1 has been waiting in RAM? So it is actually this 6 unit second that it has been waiting in RAM. So next process is P2. How long P2 has been waiting in RAM? Here you can see P2 has been assigned to CPU right when CPU has started its execution. So P2 is not waiting a single unit. Its wait time is 0. Last process is P3. How long P3 has been waiting in RAM? Here you can see in the diagram, at unit time 3, CPU has been assigned to process P3. That means P3 has been waiting for 3 unit time. Here you can see. So the average wait time, if we add the wait time of all the 3 processes and divide it with the total number of processes, the average wait time becomes 13, while in the previous case, average wait time was 17 unit second. So here we have reduced or minimized the wait time. So this refined structure of first come, first served scheduling algorithm is far better than the previous one. Now what does this show? This revised form of algorithm shows that the CPU or the system must entertain those processes first which has smaller CPU cycles in order to have better efficiency. In previous cases, we had seen the convoy effect. Convoy effect is actually the small processes behind the large ones is actually they are moving slowly, larger processes are moving slowly, and the smaller ones are waiting for them to have their way. So this effect is known as convoy effect. So we have broken the convoy effect that was being generated in the previous case of first come first served. During the previous case, P1 was the largest process and P2, P3 were the small processes, but the small processes were running slowly and waiting for the P1 to have their chance to get executed. So we have broken the convoy effect, and now the small processes are moving ahead while large processes have to go at the end. So this is the revised form of first come first served. First come first, the original form was little too costly in terms of the turnaround time and the wait time, especially the wait time. We have redesigned the first come first served algorithm, and here you can see the same example was applied in both the cases, and in this revised form wait time and the turnaround time has been reduced considerably, which was the optimization criteria that wait time and turnaround time should be minimum. I hope this revised algorithm is clear to you now. From there on, the algorithms are then designed on the basis of short processes. Those processes who have the shortest CPU cycle, so they should be given CPU first, and those processes which has the highest CPU cycle or the large CPU cycle request, they should be given CPU at the end when the smaller ones complete their execution. That is all for now. In today's discussion, we started different CPU scheduling algorithms. We'll carry on the scheduling algorithms in next lectures as well. The algorithms that we discussed today was the first come first served, and then we had reformulated or redesigned this algorithm. We have seen the efficiency and performance of CPU if first come first served algorithm is implemented. So you can see the original form of first come first served resulted in higher number of or higher amount of turnaround time and higher wait time for the process in RAM. Then we redesigned this first come first served algorithm and preferred the shorter processes first and the larger processes at the end, which then reduced the turnaround time, also the wait time. So this shorter processes is considered best as compared to the original first come first served algorithm. From there, another algorithm which is then known as shortest job first has been derived by redesigning of first come first served algorithm. We'll be discussing the shortest job first algorithm with examples in the coming lecture. But before finishing this lecture, let's see what type of scheduling is being done by first come first served algorithm. We had discussed there are two types of scheduling. Either one is preemptive or it is non-preemptive. The preemptive type of scheduling is the one in which operating system has the authority to stop a running process and take the CPU from it and assign it to some other process. This sort of processing is known as preemptive processing, while non-preemptive processing is when operating system cannot take away by force the CPU from a process. So what do you think? What sort of scheduling is first come first served algorithm? Since you have seen in both the cases, both in the original form of first come first served or in the revised form, the sequence of processes within the RAM and their appearance on the Gantt chart have not been changed. Once a process has been given CPU, it completes its execution no matter how long it is, no matter how short time it requires on CPU, but it completes its time on CPU before it goes out. So that means in both the cases, first come first served original form or its revised form, in both the forms the scheduling is actually non-preemptive. Though in first case, in the original form of first come first served, wait time was quite large. Still the processes were not interrupted in between. They were allowed to complete their execution. While in the revised case, still the processes were not interrupted in between. So all the processes are getting their complete time on CPU. No process has been stopped or interrupted. So this type of scheduling, first come first served scheduling, is actually a non-preemptive type of scheduling. In the next chapter or in the next lecture, we will discuss the shortest job first algorithm and see if it is preemptive or it is not preemptive. That is all for now. I thank you all.